All right, hello and welcome to lecture 24. This is machine learning from data. And in this lecture, we are going to talk about further extend our discussion of support vector machines. In the previous lecture, we talked about the optimal hyperplane and it was robust. Why was it robust? That's an important discussion that we will continue today. And also talk a little bit about non-separable data. And going back to the optimal hyperplane, if you remember, we said that the fattest hyperplane is the best, right? And today's lecture will focus more on why is it the best of all the hyperplanes. Um, and that is the discussion for today's lecture. A quick recap of what we said last time. So this is what we looked at in the previous lecture where we were able to find the fattest hyperplane that separates the data and tolerates most of the measurement errors. And that was the reason of the robustness of the support vectors, in the sense that this fattest hyperplane or this wide hyperplane depends only on these support vectors, which are these points that kind of define how fat we can go or how wide we can go, right? And so these data points that sit on the cushion of these margins are the support vectors. All right, so that's what we looked at last time. And then on the right hand side was the algorithm of how to get this fattest possible hyperplane. And we looked at this quadratic programming formulation of our problem in which we are trying to minimize this term, right? The weights of this hyperplane, separating hyperplane, such that it is defined by these constraints. And we try to also look at how to solve this in a certain way, how to get the variables, and we figured that these are Q, P, A, C, the four components of this quadratic program that we should be able to identify as compared to the standard form of the quadratic programming formulation, and then just solve it for my W's. All right. In the end, we also looked at this experiment where we were trying to find the support vectors and then comparing it with PLA. And what we found was obviously the comparison with PLA, as you can see, and with respect to the E out that we obtained, the support vector machines, as expected, had this E out that was quite stable, and PLA achieved at some point PLA was better off, and at some points it wasn't. And that's the entire distribution of the E outs that we obtained. Because of course, remember what is PLA doing? PLA is iteratively getting separating hyperplane, not necessarily the best one. All right. So now, as I said, today's focus is is fatter better than thin or not? And that's the focus that we are going to, that's the point that we're going to focus today. But also I wanted to look at the link of this finding the fattest hyperplane. This is the optimization problem. How does it relate to regularization? Of course, we talked about it in the previous lecture when we said that in regularization here, right, we are trying to minimize E in given some budget for my W transpose W, right? And for the optimal hyperplane, which is our support vector machines, the hyperplane that we so we are trying to minimize the hyperplane, the separation of that itself, right? And that is in some sense, if you think about it, the support vector machines are doing automatic weight decay regularization. And we also said this because the optimal hyperplane is finding the separator that has the minimum possible budget, such that and also we are able to ensure that my E in equals 0, right? So this is even a tighter way of doing regularization. And this also goes back to our discussion of Occam's razor when we said the simplest possible hypothesis is the best one. So that's exactly the implementation of the Occam's razor. So that was a link to regularization. And this tells us, because we're trying to find the best possible separating hyperplane in some sense. And so we are, as I said, regularizing in a certain way because we are trying to go towards a more robust hypothesis eventually, and not getting affected by the noise in the data, right? So as I said, optimal hyperplane is in a way simplest possible, and this is automatically doing the maximum possible regularization in some sense. So that's what the link to regularization determined. that there is like this direct link to regularization. All right. So now going back to the topic for today, which is like the larger margin or the fattest hyperplane is better, and how will we look at that? So obviously the question I'm trying to answer is the fattest hyperplane better, and how do we find that? So what we're doing is we are following this like 3-step approach, right? And in each of the steps we will try to explore some aspect of what's really going on in a learning problem and why are we trying to find the largest margin, right? The very first one is the experimental, as you can see here. So we're trying to like experimentally perform essentially an experiment to establish my E out, right? And then see what happens when I'm kind of getting some other hyperplane as compared to the fattest hyperplane, and then comparing the results. The second one is more like a theoretical basis for finding whether the fattest one is the best. And now, what we're doing is like fat separators can have a smaller VC dimension than thin separators. So if we are able to establish that, then we know that we'll have a good link from E in to E out, right? And based on that, we'll establish like whether like wider separators or larger margin are better than the thin margins. And the third one is that we're looking at this cross validation error. In specific, we will get a bound on the cross validation error for the optimal hyperplane that does not like explicitly depend on the dimension of the data. Because remember, like the cross validation error is an estimate, or I would rather say unbiased estimate of out of sample error. And we can come up with a bound that is only dependent on the support vectors and not the entire data. And that in turn, or that in like in some ways will help us establish that yeah, yes, that is evidence that larger is better. All right. So in conclusion, like in summary, 3 pieces of evidence will help us get an idea of whether fatter is better or not. So let's move on to the very first one. That's like the experimental evidence. So what is this experimental evidence that larger is better? So there was this experiment, of course, derived from the book where there is like some data set that's given to us, and let me draw it here. And then I'll show you the actual picture, of course. But let's say these are the 2 regions that I have, like separated by my target function. And so let's say I have like some plus here and sorry, cross here, and this is like, let's say -1 region, and this is my +1 region, and then there is this thing, maybe like something like this. All right. And so what we are trying to do in this case is like generate. So for like the experiment was done for n equals 20, but I'm just like showing you what's going on here. So what we can do here, as you can tell just by looking at like any data set rather, that we can generate a separating hyperplane just like we did in PLA, and there could be many of them, right? So step 1, let me write it like step by step. Step 1, let's generate a separable data set with n equals 20. So data set that's separable, and I already said n equals 20. So that's step 1. And then in step 2 of the experiment, right, randomly generate around 50,000 separating hyperplanes for that data set, right? So randomly, and like by randomly, it means like with some different B's and some W's, you'll get like different separating hyperplanes, right? So randomly generate 50K hyperplanes, separating hyperplanes. All right, so here we have step 2. Now for step 3, what I'm going to do is I'm going to compute the maximum possible margin, right? The fatness. And I have the formula for that. We did that last time. And so I'm going to use that, right? So the third step is like go and compute for each of these the fatness. So for instance, for the first hyperplane, which I'm denoting by H1, I'll compute the fatness, and that is going to be gamma of H1. And then let's say for the second one, I'm going to have gamma of H2 and so on up to like the 50K, right? Gamma of H 50K. All right. So here, like what we'll do is we'll try to we'll also have like this fattest possible hyperplane, and we know how to do that because we formalized the optimization problem for that, right? So what we are going to do is we will also try to fit the fattest hyperplane here. And